Okay, here we go. This is my first attempt at recording a lecture for Flipped Classroom. This is for the first reading/listening homework assignment for CS 262. So this is going to cover propositional logic. So here's the outline: logical sentences, interpretations, the operations you can apply, which includes a little aside on the paradox of material implication. We've also got tautology, self-contradiction, sound rules of inference, De Morgan's law, and then some stuff about the validity of an argument. So let's start with logical sentences. So logic, one thing to note about logic is logic doesn't actually have to reflect anything about real life. So we're in the world of logic. It was created by mathematicians and philosophers in order to achieve a type of reasoning. So it doesn't really have to relate to or reflect the real world. And in fact, I've found it easier just, as a logician, just to kind of ignore the real world and not worry about it. So a lot of times you'll be reading some logic examples, and it'll be like some statement P, and the statement P will be P is raining, and you look outside and be like, hey, it's not raining. But that doesn't really matter. You don't really care. You just care within the world of logic that's being defined for that particular example. So logic's going to consist of sentences. Sentences are sometimes called propositions. They're sometimes called statements. The fact that they're often called propositions is what leads to the term propositional logic, which is the type of logic that we're studying. And from a computer science perspective, you can think of these kind of like variables, the sorts of variables you would use in a programming language. In propositional logic, these variables, or propositions, statements, or sentences, they can only be true or false. So there's only two possible values. They're basically like Booleans. So they can be represented by any letter, like P, Q, or R. Sometimes they're actual sentences, like Amy Poehler is hilarious, or the London Olympics are not in any way marred by fog or terrible food, or it's raining. And those sentences can either be true or false, except for Amy Poehler is hilarious, which I think is universally defined to be true because Parks and Rec is so funny. That was a joke, by the way. I know this is a recording, so you can't see my body language, but that was a joke. I mean, I do think Amy Poehler is hilarious, but that sentence doesn't necessarily have to always be true. In the world of logic, it could be true or false. Okay, moving on. So some notes about sentences. Again, these don't really have anything to do with the real world, so it's raining is just a sentence. Doesn't matter what the actual weather is today. These sentences can be combined using logical operators like and, or, not, and so on. In general, this means that your basic sentences, if you're going to represent them as sentences, like as actual, words, probably shouldn't have the words and, or not in them. Otherwise, it gets very confusing when you see the word and. You're like, well, is that part of the sentence, or is that a logical operation? So we want to keep the sentences simple and declarative, kind of like a good FP paper. So let's talk about interpretations. So an interpretation is an assignment of true or false to all of the sentences that we have for a particular example. And once again, logic doesn't really care if these sentences are true or false in real life. And one way that I've found that's helpful to think about this, different interpretations, these could represent different days. In other words, it's raining, today is true, tomorrow might be false because it stops raining. It could be different opinions, different people might disagree, could be happening in different time zones, there could be parallel universes, whatever. So suppose we have two sentences, P and Q. This gives us four possible interpretations, and here I've drawn out a truth table to give you some examples of what they are. So we've got P, which can either be false or true, and Q, which can either be false or true, and there's actually four possible interpretations, and I hope my cursor's showing up. You can see here we've got false, 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 true, true, false, true, true. Those are the only possibilities. So there's four possible interpretations if there's two variables, P and Q. So let's talk about some of the operations. So there's a bunch of operations you can apply to these different sentences. You've got not, you've got and, you've got or, you've got IFF, if and only if, sometimes also called equality or biconditional, and then you've got implies or material implication. And these symbols, or the symbols for these operations, show up displayed differently depending on the context you're in. Not, computer scientists will represent it as an exclamation. Logicians sometimes as like a tilde. Sometimes you'll, mathematicians or logicians, sometimes it's sort of a symbol that looks kind of like that. And sometimes is sort of a caret sign, but you might also see an ampersand or two ampersands, or is sometimes sort of like a V, but you'll sometimes see a vertical bar or two vertical bars. If and only if, you'll sometimes see written IFF. Sometimes you'll also see it written as sort of like a double arrows, and implies is almost always a single arrow of some kind pointing in the direction of the implication. I can't entirely remember which notation. I'm going to try to use the sort of V and the caret for and or. But if you see different notations, that's basically what it means. There's some flexibility for how the notation needs to be written. So here we have the four major different operations that we just talked about, and, or, material implication, and if and only if. We're not showing not obviously, like if P is true, not P is false, and if P is false, not P is true. So that's not really a complicated one. We've got P and Q, and here we've got P and Q. So I went ahead and sort of broke these out and highlighted each one in blue. So P and Q is only true when both P and Q are true. So you can see true here. For P and Q to be true, if either P or true is false, then we're looking at false. For or, just one of them has to be true. So as long as one of them's true, P or Q is true. For implies, I'm going to kind of return to this, but the general idea here, if P implies Q, the only way to make that false is for P to be true and Q to be false. Now, it's kind of not necessarily intuitive why it's the case that P implies Q is just true if P isn't even true. I'll return to that. This is called the paradox of material implication. And then here we have P if and only if Q, or P is equivalent to Q. And so for this, you can see if P and Q are both false, this is true. And if P and Q are both true, this is true. Otherwise, it's going to be false. So that's if and only if. And so I want to do a little aside here for this paradox of material implication. This is a construct used in logic. It's often pronounced if P then Q, but implication is not the same as causality. In fact, it's not really related to causality at all. It's a logical construct, material implication, given an antecedent, an if part, and a consequent, a then part. If the antecedent's false, we can't make any claims about the consequent. And so since we can't show the consequent is false, we have to say the whole sentence is true. So this is sort of like a default. If you've got P implies Q, and P isn't even true, well then you can't really conclude anything about the whole statement, so by default it's just going to be true. And in English, believe it or not, there's a common rhetorical flourish when people are talking that comes out of this. So you'll sometimes hear people say, like, if you're able to increase spending while simultaneously decreasing taxes, then I'm the king of England. Or like, well, if you're 7 feet tall, then I'm the king of England, or something like that. And what this is doing is it's highlighting the idea that the antecedent, in other words, the then part, is so, the antecedent, the if part, is so ridiculously false, it's not even worth considering the then part, the consequent. And so down here, I've actually got a link to a little bit more of a description of this, a philosopher writing a little bit of stuff about the paradox of material implications. So, once again, this little rhetorical flourish, if X, where I strongly believe X to be false, then something that's obviously false, like I'm the king of England. In fact, I'm not the king of England, it turns out. So that's the paradox of material implication. And just to kind of return here, remember, one more. If P implies Q, the only way to make this false is to show that P is true and Q is false. Obviously, if they're both true, it's going to be true. And as soon as we see that P is false, then the entire thing just by default is true. And so that's because of the way material implication works. Again, it has nothing to do with causality, and it's not the same as an if-then in computer science. So let's talk about tautologies and self-contradictions, or as I like to call it, the Hamlet rule. A tautology is an expression that's true in all possible interpretations. So it doesn't matter how you assign the sentences to true and false, a particular statement is going to be true. So simplest example I can think of, to be or not to be. So I'm sort of considering to be, I'm writing it as like to be, so that's like a sentence. And I've got to be or not to be. And so, of course, I'm taking that from Shakespeare's Hamlet. And here I'm making fun of Hamlet. Okay, Hamlet, yeah, one of those is true. Now, go get your revenge and get this, 4-hour-long, 5-act play over with already. To be or not to be, another famous one, if you ever get on an elevator, like at a math conference, with a bunch of mathematicians, and you say, is this elevator going up or down? They'll always answer yes. And you'll be like, what? And they're like, well, we don't have any elevators that go sideways, so this elevator's either going up or it's going down. One of those must be true, so clearly, the elevator's going up or down. So it doesn't matter what interpretation. Both of those are going to be true. Self-contradiction, on the other hand, this is false in all possible interpretations. So the simple example here, to be and not to be. Well, for an and to be true, you would need both parts to be true, and it's not possible for to be and not to be both to be true. So that's the simplest example I can think of a self-contradiction. And just to kind of, not to belabor the point, but to draw this out a little bit more, so suppose to be is a variable. Well, if to be is true, then not to be is false, but to be or not to be is going to be true. Similarly, if to be is false, then not to be is true, and so to be or not to be is true. But to be and not to be is going to be false in both instances, because one of these has to be false because one is the negation of the other. So that's a couple of examples of tautologies and self-contradictions. So let's talk about some rules of inference. So a rule of inference, this allows us to combine expressions together and to simplify them. And what's great about this is once we've shown that a rule of inference is sound, we can actually apply it any time it fits our facts or sentences that we have at our disposal. We can actually show many of these rules of inference by truth table, but I'm going to leave this as an exercise for you. I'm not actually going to show all of that. So here are four really famous, the four best-known examples of rules of inference. Modus ponens, MP. So if we know that P implies Q, and we know that P is true, from that we can conclude Q. And this is a sound rule of inference. Anytime you have P implies Q and P, for any P and Q, you can always just go ahead and conclude Q. Modus tollens, similar example, if we know P implies Q, and we know that not Q, then we can conclude not P. Equivalence elimination, if we know P if and only if Q, this actually means that P implies Q and also Q implies P. And then double negation, if we know not P, we can conclude from that P. So these are sound rules of inference. In fact, there's 9 rules of inference and 10 rules of replacement, and here are a couple of links to those. So you may want to go ahead and click through here and take a look at these. What's great is that these rules, these can actually be used to prove any valid conclusion that has at least one premise. I probably should... Well, probably the simplest thing to do is go ahead and show these by truth table. I don't know if I have that in here in these slides, but you want to go ahead and show that these are true. At least modus ponens is true using a truth table. So let's talk about De Morgan's law. So De Morgan's law, this is probably the most popular rule of replacement. If we have not A or B, this is the same as saying not A and not B. And similarly, if we have not A and B, this is the same as saying not A or not B. So you can sort of think of it as like, well, if I want to take this not and sort of distribute it inside these parentheses where there's an or, well, what I do is I flip the or to an and then I apply the not to both of the things, and that kind of breaks out the parentheses, and then the same thing down here. And what's fantastic about De Morgan's law, this is true even if A is itself some complicated expression like P and Q or Z or something like that, and maybe B is some complicated logical expression. That's okay. you can go ahead and do this. And then if you need to recursively apply the not to A, where maybe, A is some complicated expression, you can totally go ahead and do that. And I'm, again, going to leave it to you to go ahead and show that these are equivalent with the truth table. It's not particularly hard to do, but, it's a good activity. You should probably go ahead and give that a try. So now let's talk about the validity of an argument. So an argument will have one or more premises and a conclusion. And an argument's valid if all interpretations that make the premises true also make the conclusion true. So I'll say that again. All interpretations, in other words, all possible assignments of true or false to all of the sentences, all of those that make all the premises true also make the conclusion true. And this is actually a hilarious video. This is Monty Python. It's called The Argument Clinic. It's a few minutes long. I recommend checking it out. It's kind of an example of, when logicians and mathematicians and philosophers say an argument, they don't actually mean like two people yelling at each other like you're watching, cable news or something like that. What they mean is a very specific and precise type of logical reasoning according to some formal rules. For example, propositional logic, which we're learning today, or first-order logic, which we'll learn shortly. But the video is really funny, so I definitely recommend checking it out. So there's three ways you can show an argument is valid. One way is just use a truth table and then just go through and check. Okay, all these interpretations make the premises true. Do they also make the conclusion true? You can apply sound rules of inference, either the 9 rules of inference that we have seen, well, the 4 that we've seen and the 5 that we didn't see that we had a link to. We could apply these to the premises to derive the conclusion. Or you can do a proof by contradiction. You can assume the negation of the conclusion. Then you can apply rules of inference that reason to a self-contradiction. For example, A and not A, or something like that, something that can't possibly be true. So we know modus ponens is a valid rule of inference. So we know this because we've been told this, but let's go ahead and pretend we didn't know that, and we're going to want to show this. So P implies Q. And P, those are our premises, and the conclusion we're trying to show is Q. So what we want to do is show that all interpretations that make P implies Q and P true also make Q true. That would mean it's a valid rule of inference. Well, we can show this by truth table. There's only 2 sentences, P and Q. So here's our 4 possible interpretations. And then we've also got P implies Q, and we can this is just material implication. We'll just go ahead and set this up. And so we can see, well, what makes both the premises true? Well, P implies Q is true in this interpretation, and P is true in this interpretation. In fact, those are the only ones, that's the only line of this truth table that makes both of the premises true. And in that interpretation, the conclusion's also true. So everything that makes the premises true also makes the conclusion true. Therefore, this is a valid rule of inference, and that's all we have to do. Now that we've shown that modus ponens is valid, anywhere we have 2 sentences and we know that one of them implies the other one, and that first one's also true, we can just go ahead and apply modus ponens. We're good to go. It's pretty awesome. Here's an example of an invalid rule of inference. P implies Q, so if we know that's true, and Q, so we know that's true. We can't conclude P from this, and the reason for that is, well, here's an interpretation that makes both of the premises, P implies Q and Q, true. That would be this here, and in that one, the conclusion that we're trying to show is also true. But here's one that isn't the case. P implies Q is true, and Q is true here, so the premises are true, but the conclusion's not true. So for an argument to be valid, every interpretation that makes both of the premises true must also make the conclusion true. This does not make the conclusion true, this one example here. So that one example there, that screws the whole thing up. This is not a valid rule of inference. This is an invalid rule of inference. And this is just a couple of useful validities that I wanted to mention. P implies Q is equivalent to saying not P or Q. And P implies Q is also equivalent to saying not Q implies P. I think it's the same as not. No, damn it. I think it's not Q implies not P. I think this slide is wrong. Well, okay, how about this? check this slide and see if it's right or wrong, whether this is right or whether this is right. I think that's all I have. Oh, one other question. What are the limitations of propositional logic? So, we've seen propositional logic. It's pretty powerful, but it does have limitations, and in fact, it has important limitations, which we're going to get around, or not get around, but which we're going to address by increasingly more powerful systems. But go ahead and think about what some of these limitations might be. Thank you.